Well, now let's talk about functions. What we learned so far. Let us review what we learned throughout these chapters. Let's connect the dots. So, review. In discrete math, we start talking about logic. How do we connect statements together? After talking about logics, compound statements, connecting the statements together, we're interested in talking about numbers. Number theory. In number theory, we dealt with natural numbers, we dealt with integers, we dealt with fractions, rationals, and we tried to construct operators and using that operators to talk about theorems, propositions, lemma. Then we said, okay, now let us consider collection of numbers, and we moved on to set theory. Set theory. Set theory helped us to actually see the collection of numbers and objects together, and we define operators like union, intersection, complement, set difference to build some new objects. Now we're going to talk about functions. Functions act like machine. They take on sets, values in sets, and they make some changes, or they might not even make any changes to those sets, and they give us some outputs. So our focus is on functions. Functions on sets. Elements of sets in our math class are numbers. Very well. So we are on chapter 7. 7.1. We are on page 1. Okay, very well. Functions. We talked about functions in chapter 1. Well, remember that when we talk about functions, we said that, hey, functions in discrete math are different from functions in calculus. In calculus, we have like the plane path in the sky. But in discrete math, we're interested in pixels on screen. Dot, dot, dot. Discontinuous graphs. So recall that we have 2 to the n and 2 to the x as 2 different types of functions. And we are saying that, hey, you have 2 to the n. N is a natural number, so it doesn't take on all values in between 1 and 2, in between 2 and 3, in between 3 and 4. You see gaps on the horizontal axis. So if you use x-axis, and y-axis, 2 to the n, the very first value that you're allowed to plug in is 1. So when your n is 1, your y value is 2 to the first power, which is 2. Very well, okay. This is my very first point on the graph of this function. The second one is going to be 2. If I plug in 2, I get 2 squared or 4. Well, this is my second dot, and I can continue plug in more values, and the behavior of this graph is going to be like this: 3 and 8, and so on. So you see dots representing the graph of this function, and this graph is discontinuous. We have gaps in between. We're not allowed to connect these dots. But in calculus, x belongs to R, real numbers. All these gaps will be filled. There we go. So we have x-axis, then we have y-axis, and when we try to graph this function, the graph is going to be like this. Well, if I plug in 0, I get 1. If I plug in 1, I get 2. I can plug in negative numbers as well because x belongs to real set. So the graph is going to be a continuous graph. And this is the behavior. It goes up. So let me just show you. This guy continues. And there is no gap. This is the graph of this function. Both of them are functions. Don't take me wrong here. Both of these are functions. This is a discontinuous function. This is a discrete function. And this is a continuous function. Remember that. In calculus, you had a test. If you have a graph, that graph represents a function if it passes vertical line test. And remember, we use that vertical line test to define a function. So recall, in calculus, we say a graph represents a function if it passes vertical line test. It means that if I have a vertical line, any vertical line, there is at most one intersection between that vertical line and the graph of the equation or the relation that I have. Otherwise, it's not a function. So, definition. When we are talking about functions in discrete math, we need to specify the domain and the set of possible outputs, co-domain. A function from set X to set Y, denoted by F, that takes on values from X and maps them to Y, is a relation. We call the relation is a relation between X and Y. From set X, which we call the domain, to set Y, which we call codomain. We're not talking about the range yet. We're just saying that, hey, we have codomain. So do we have any condition, or is this guy just a subset of Cartesian product? So far we mentioned that. What are we saying? We're saying that we have a relation. What's the meaning of that? It means that, so this part means that F is a subset of Cartesian product between X and Y. Remember that Cartesian product between x and y is the collection of all ordered pairs like x and y, such that x belongs to the first set and y belongs to the second set. Okay, so we have a domain, the first set, and the codomain, second set. What is the condition? First of all, every element in x is related to some elements in y, such that every element in x is related to some elements in y. This is the very first condition. Then no element in x is related to more than one element in y. No element in x is related to more than one element in y. So what's the meaning of these two here? It means that the graph passes vertical line test. Equivalently, the vertical line test is met. So remember that the definition was like this. If you have f of x equals to y and f of x equal to z, then you can conclude that y and z are equal to each other. Okay, this is what we learned before about a function. Again, a function acts like a machine. This is the machine that you have. F as a machine. You plug in some values. Machine. You plug in some values, input values from x, inputs. This machine acts on those input values and it gives you some outputs. Think about F as a cooking recipe. You have some ingredients like flour, like vanilla, sugar, salt, egg, milk. You combine them together using your F, your function, your instruction, your machine, and then the outputs are cookies. Okay, so we defined a function. Now, okay, what do we do with the function? Well, we're going to define something new. So, new definitions. When it comes to this chapter, we're going to deal with these definitions a lot. So I'm going to write all of them down here so you can distinguish between them. First of all, you need to have a function. Let f from x to y be a function. So we usually say that function f maps element from X into Y. We say F maps elements from X to Y. So X to Y. So the word that we're using is maps. Function F maps element from X to Y. And we write them usually this way. We say that X is mapped to Y by using this arrow and putting a little small vertical line here attached to the arrow that we are dealing with members elements. So these are sets. These are sets. Set X, set Y, and these are the elements members in those sets. Well, the image of set X under F, so the image of set X under F, denoted by F of X, which is a set. This is defined as the set of all Y values, the set of all Y values in the codomain such that Y is equal to F of X for some X in set X. Okay. Now, let Y be a member of set Y. The inverse image of Y, inverse image of this little member Y is denoted by F with -1 as its exponent, but we're not talking about the inverse function. We're just talking about inverse image. So the terminology that we're using is inverse image. Inverse image of Y is equal to the set of all X values in the first set, such that F of X is equal to Y. So this set F of X equals to all Y values in the codomain. Remember that this Y is not the range. This is a codomain. Such that Y is equal to F of X for some X in X is called the range of your function. Well, the inverse image of one element, this is just a member, one member. Now I expect you to ask, why did you define the inverse image of a set? Well, we can do that. Let set C be a subset of your codomain. The inverse image of set C is defined this way. Inverse image of C is equal to the set of all X values in the domain such that F of X is a member of set C. So note the difference between these two. Then you have one member, F of X, is equal to that number. When you have a set, this is a set, then f of x belongs to that set. The difference between these two. Okay, give us an example. We keep talking about abstract materials. Well, consider this relation. Example. Suppose you have the first set, we're going to use arrow, x1, x2, x3, and x4. And I have my second set, codomain, set y, y1, y2, y5, y1, y2, y3, y4, y5, and then x1 goes to y3, x2 maps to y1, x3 maps to y3, x4 maps to y4. So this is your recipe. This is your machine, F, that maps element from X into Y. So this is your domain, and this is your codomain. First of all, do you have a function? Is this a function? B. What if I ask you to find the inverse image of one element, y sub 3? What if I ask you to find the inverse image of the set including y3 and y4? How do we answer these questions? Perfect. So is this a function? Yes, of course, it is a function. Okay, each value in the domain is connected to some element in the codomain. x1 to y3, x to y1, x3 to y3, x4 to y4, and so on. And okay, does it pass vertical line test? Okay. So x1 goes to y3, x3 goes to y3 as well. Okay, we don't have any problem with that. x2 goes to y1 and x4 goes to y4. They have a nice function here. Very well. So what is the inverse image of one element? Remember that we're discussing this definition. The inverse image of just one element is defined as a set. Guys, make sure you have the set notation here. So I'm going to put this guy using a different color. So you know that you are following the exact definition of having the set notation. All x values such that f of x is equal to y. So what is my y here? What is my one element is y3. What are the elements in x that are mapped into y3? The elements in the domain that are mapped into y3 are two elements, x1 and x sub 3. So I'm using set notation, the set of all elements, x1, comma, x sub 3. Well, inverse image of one element. In part C, it says, hey, now what is the inverse image of this set? Here you have a set, including y3 and y4. Again, take a look at the definition. The inverse image of a set is another set. So we don't forget about the set notation. We're using our curly brackets. Here we go. And okay, so we're looking for elements in the domain such that when F takes those elements belong to set C. So F takes those elements and they are member of C. Okay, they are member of C. What is F of 1? F of 1 is equal to Y3. Y3 belongs to this set. So the first one is X sub 1. Okay, what about X sub 2? X sub 2 is equal to Y1, but Y1 is not a member here. So we don't need X3. Now we don't need X2. What about X3? X3 is mapped into Y3. Y3 is a member here. So the next member is X sub 3, comma. What about X sub 4? X sub 4 is mapped by F to Y3. Y3 is a member of this set. So it's going to be another element in this set. So the results are all sets. So your turn. Suppose I give you this recipe here. I ask you, what's the answer to these questions? Here you have an arrow diagram. The elements in set X are A, B, C, and the elements in the second set or your codomain are 1, 2, 3, 4. 1, 2, 3, 4. And this recipe here, this machine here, maps A into 2. It maps B to 4. And it also maps C to 2. Okay, question says, find the inverse image of 2. What is the inverse image of 2? What is the inverse image of 4? What is the inverse image of 3? Okay. So the inverse image of 2, remember that inverse image of an element, inverse image of a set, they are both sets. So we're going to use set notation. So 2 is connected to 2 elements in the domain A and C. So we have to list both of them. Inverse image of 3, well, 3 is a member in the codomain, but it's not connected to anything in your domain. Consider you're cooking chocolate cookie and the recipe says, hey, you have a glass. Well, glass doesn't fit into the elements in your input values. It's just there. So the set of nothing, it means that you have an empty set. What about the inverse image of 4? 4 is connected to B in the domain, so you're going to use set notation and put B in it. So what if I ask you to define this set as a collection of ordered pairs? How do you write it down? So remember that this is a function, and this function F is a collection of ordered pairs that they satisfy vertical line test or those 2 conditions that we mentioned before. So what do we have here? The very first pair is A, comma 2. The second pair is b comma 4. The third pair is c comma 2. This is how you write your function in ordered pairs. So this is my function. Remember that in chapter 1, we said any function is a relation that satisfies some conditions. So this is a function, the first pair, the first order pair, the second order pair, and the third order pair. Question for you before writing the next theorem. I have a question. I ask you this: are these two equal to each other? Are these two functions equal? So the very first function is f of x equals to x squared minus 1 divided by x minus 1. And the second one, g of x, is equal to x plus 1. Are these two equal to each other? Yes. Very well. So what do we have here? We have a rational expression. We have x squared minus 1 divided by x minus 1. You might say, hey, I can simplify this as x minus 1 times x plus 1, and it's divided by x minus 1, and you can cancel out the common terms. And after simplifying these two, they are the same. X plus 1 is equal to x plus 1. So it says, since the expressions are the same, the functions are the same. Well, you have to stop a little bit. The domain of function f includes, we do not evaluate the domain after simplification. We have to forget about simplification and get back to the original function when we're talking about the domain of the function. The domain of this function is the set of all x values such that the domain is never 0. X minus 1 cannot be 0. So what is the domain? Domain is all real values except for 1. So this is 1. They have to exclude 1 from the real line, and this is the domain of your function. But for this time, here you have a linear expression. Linear expression, nice function. When you have a nice function, the domain is R. Everything is acceptable. So if you want to visualize this, you just shape the real line from negative infinity to positive infinity. So since they have different domains, these two functions are not equal to each other. These two functions are not equal because of the domains. Very well. So what we learned so far, we learned that if the function, the expression, the output values of the function, if they are equal to each other, it doesn't mean that two functions are the same. We have to be careful about the domain as well. So in general, we can define this theorem. This theorem says let f from x to y and g from x to y be two functions. Again, I'm going to highlight the domains so you know that the domains are the same. X and x. F as a relation is equal to G as a relation if and only if f of x is equal to f of G, f of x is equal to G of x for all elements in domain X. So what's the difference between these two? Here I have f equals to G. It means that the set of ordered pairs is equal to this set of ordered pairs. Set of ordered pairs. Ordered pairs if and only if the formulas are the same. So domains are the same. These two sets are equal to each other if and only if the formulas are equal to each other. Definition of identity function. So let x be a set. Answer me this. Have you seen this graph before? Suppose this is graph. X-axis, and this is my y-axis, and I have some points. These are my points. 0, 0, 1 and 1, 2 and 2, 3 and 3, negative 1 and negative 1, negative 2 and negative 2, negative 3 and negative 3. How do we define this function? What is the name of this function? So 0, 0, 1, 1, 2, 2, 3, 3, minus 1 and minus 1, minus 2 and minus 2, and so on. How do we define this function? What is the definition of this function? What's the name of this function? This function is called identity function. So let x be a set. Identity function denoted by I sub x takes elements from set x and map them exactly to set x. The formula, the definition for this function is Ix at any value gives you the same input as the output. Input and outputs are the same. Outputs are the same. So the graph, the discrete graph is going to be dots like this. Remember in calculus, you have this graph. In calculus, you say, hey, I have y equals to x. The graph is like this. The identity function is line y equals to x. X and y are the same. In calculus, in discrete math. You have seen this before. You might not know the name for this function. We call it identity function. Where do we use it? In composition of functions. One question for you. In your opinion, if I write something like this, is this give me a function? So I'm going to write down something. My professor asked me to come up with a function. I'm going to tell my instructor that this is a function question. But I want your opinion as my colleagues. So question, is this a function? If not, what's wrong with it? So I'm going to say, well, I'm going to define f that maps rational numbers into z integers, and I'm going to define it this way. I'm going to say, hey, f takes fractions and the output values are the numerators. So function f takes fractions, these are fractions, from rational set, and it gives me the output values are the numerators. So as my colleagues, do you think this is a function? If not, help me. If not, what's wrong with this? So remember that when we defined a function, we said that the definition of function was this. F maps domain into codomain, and it has to have two conditions. First of all, any element in X, any X in X, is mapped to some element in Y. Is mapped to some element in Y. And then, so let's check the first condition. It says, hey, elements in Q, fractions, are mapped to integers like M. Okay, the second condition says, hey, if f of x is equal to y and f of x is equal to z, then for sure you can conclude that y and z are the same. It means that it passes vertical line test. Okay. Well, f of x is equal to y, f of x is equal to z. Okay, y is equal to z. So what's wrong here? Is the second condition met? Can you come up with two fractions that they give you the same z values? Any idea? Anything about it? Something to think of? Two fourths and a half. Very good, very good. So think about it this way. Well, so f of a half is equal to 1, right? Okay. What else do we have? Can I use f of 2/4, which is 2, then y and z? Note that these two numbers are basically the same. 2/4 is equal to 1/2, right? After simplifying them. And I didn't impose any condition here. So f of 1/2, f of 2/4. X values are the same, but y values are different from each other. 1 is different from 2. In this case, we say that this is not well defined. Here, this is not well defined. So if one of these two conditions are not met, then you say that you don't have a well-defined function. It's not even a function. You can come up with different examples and reach the same contradiction.